you all. I am Priya Vinayak. I have finished my PhD from Indian Institute of Technology, Delhi this year, and I am currently working with the electronic design automation team of Synopsis. And my topic for PhD was electrochemical detection of heavy metal ion in water samples. So that is why I have chosen electrochemical impedance spectroscopy, because this has been analyzed for a long time, and there are multiple new applications that has been explored using electrochemical impedance spectroscopy. And since we all know about the basics of it, it's very important to understand very keen points that I have observed during my PhD journey. Some points that we may have missed while reading a tutorial or while doing some experiments, and how important those experiment points are when you are actually taking the measurements. So when I say electrochemical impedance spectroscopy, this is what we all see in our mind, that there should be a electrochemical cell there where there will be 3 electrode, reference electrode, counter electrode, working electrode, and we will be analyzing Nyquist plot or Bode plot, right? This is like the basic image of electrochemical impedance spectroscopy. For most of the cells that, or most of the application for which we are exploring this EIS measurements, but it's a bit more than that, and the Nyquist plot and Bode plot are the most easiest to analyze when it comes to electronic or electrical circuit fields. So we start with this, like when there are so many electrochemical technique which are available to work in different applications that we are exploring with electrochemical impedance spectroscopy, why we have particularly chosen EIS for all these applications, and why EIS is important as compared to the other application. So when I talk about other techniques such as linear sweep voltammetry or cyclic voltammetry, people have used those techniques for the battery, to check the charging, discharging, or some other measurement in battery technologies, in corrosion or in sensing application. But when we come to electrochemical impedance spectroscopy, the major difference between other technique and this technique is, this is not time dependent technique. This is actually frequency dependent technique, and we can probe very slow measurement and very fast measurement with utmost accuracy. So it is important that if we want to precisely check a system at lower or higher frequencies based upon the slower or the faster processes, we also probe that particular application with EIS as compared to other application. So most of the recent application area for EIS are the energy storage conversion. We all know that fuel cell has been in talks for like a long time now, and the most important technique which is used for the characterization of fuel cells are electrochemical impedance spectroscopy. Next are the supercapacitor, which work as capacitor, but there are some techniques which are very important to be probed using EIS, because we need to check them how supercapacitor behave at a certain frequency levels. Next are the solar cells, and if we come to biomedical application, glucose sensing is the most important thing that we are using as of now, and this is one of the initial techniques which have used this EIS. Next is the drug delivery system. Also we used EIS measurement for water quality analysis. Most important field where we are using EIS currently are the batteries and the corrosion system, because in batteries, when we are charging and discharging, we are coming up with so many new kind of lithium ion batteries and some replacement for different cathodes and anodes, but it is very important to check the time period and for how long these batteries are going to sustain, because we want to use them for EV vehicles or some other application where the charging and the discharging time should be very much relevant. So to start with, and EIS, sorry for a very busy presentation, but there was a lot to talk about, and you may have missed my talking, but you can always read. So what is actually an electrochemical impedance spectroscopy? This is actually a transfer function technique in which is actually linear time invariant system. The first thing that we should be realizing before taking an electrochemical impedance spectroscopy measurement is that anything that you are probing in your experiment should not be changing with time, that the system should be linearly time invariant, it should be stable. There should not be a chance that so there are some processes which are changing with time and we are probing it. In that case, we will not be getting the repeatable data for these kind of measurements. So that is why we said EIS is actually a transfer function technique which model the output signal based upon the input AC signal that we are probing. In case of other measurement that we are taking with electrochemical techniques, we are actually applying a DC voltage, but in case of an EIS, we are actually superimposing an AC voltage over a DC voltage. We are applying an AC signal, and we are also measuring, or we are also we are also getting the response in the frequency domain. So that is why we will not be dealing with xt or yt, that is the input and output signal. We will actually be dealing with x naught sine omega t or y naught sine omega t, which are our frequency dependent signals, input and output signals. So why EIS is important? Because this is one of the only technique which offers a kinetic and mechanistic data of various electrochemical system, and you can always, the data that we'll be getting at the end of an EIS measurement can be converted or deconvoluted in the form of an electrical circuit. As an electrical engineers, or it is very important for us to, you know, and very easy for us to understand an electrochemical circuit in terms of resistor, capacitor or inductors, as compared to the electrochemical processes which are happening at the surface of the electrode or in the electrolyte. So that is why the major aim of getting into an EIS technique is whatever data we are getting in terms of Nyquist plot or body plot, we have to convert that data in the form of equivalent circuit, or we known them as Randall's equivalent circuit, so that we can analyze that circuit in terms of resistance and capacitance, and we can compare the data for all the application based upon these passive elements only. So important consideration, again I have already mentioned that it's a linear time invariant system. Nothing should be changed while taking the measurement. The system should be kept stable and there should not be any kind of movement, or it should not be happening that the working electrode that we are using is running out of electrolyte or something, because in some cases we have to take very long measurements, especially in case of batteries, because the measurement can go for a long time, and it's very important to keep that system stable. If the system is not stable, the data that we are getting in terms of charging and discharging will not be able to repeat it in the longer term. So basically the response of an electrochemical system depends upon the resistance of the liquid electrolyte. So when I said in case of an EIS measurements, it's a electrochemical cell in which we see three different kind of electrodes. That is the main vision of all of us when we think about EIS. So all these electrodes, they are kept inside a electrolyte, because it is very important that the measurement that we are taking, there should be a conducting media. So that electrolyte is actually a conducting media, but that resistance of that electrolyte media is very important. For example, if I was working with the electrochemical sensors, and initially I was keeping the concentration of my electrolyte as 0.01 molar KCl solution in buffer, but I was not able to get the measurement, because whatever processes were happening at my electrode surface, they were hampered by the resistance of the electrolyte. So we shift to 0.1 molar. In some cases, I checked the literature, many people have taken the measurement with 0.01 molar. There is no standard case. So whenever we think about taking a measurement, it is very important that we understand what is the conductivity of our electrode for which we are going to take the measurement. In some cases, the resistance or the conductance of the electrode may hamper with the resistance or conductance of the electrolyte. So the response of the electrochemical system, it depends upon the resistance of a liquid electrolyte. So it is very important the electrolyte that we are using, it should be kept constant throughout all the measurement that we are going to take. Next is there are different bulk and grain boundaries conductivity, because in case of an batteries, we are not going to use a direct liquid electrolyte. We are going to use liquid electrolyte that can get converted into solid electrolyte kind of a thing, or a polycrystalline based upon you know how charged your battery is. So sometimes there is an accumulation of some charges near your anode surface, and that solid kind of an electrolyte, it can hamper the performance of the device, and then the response that we are going to get will actually be the response based upon the conductivity of that electrolyte as compared to the bulk, or as compared to the actual battery setup. So the other important parameter for an electrochemical system is the charging and discharging of the electric double layer, because when we are taking the measurement, there are many interfaces that are forming in an electrochemical cell. One is your electrode to electrolyte interface, which is important. That interface is formed at all the electrode that we are using, but we are more concerned about the working electrode and electrolyte interface. So when there is an interface forming, there are always a chance that there are some kind of charge that are going to get accumulated at that working electrode, because we are going to apply some voltage over there, and when those electrodes when those ions they are getting attracted toward your electrode from the electrolyte, there will be a formation of double layer charge, that is a capacitor. And if the value of that capacitor is very similar to your response of your processes in your electrochemical system, then it will be difficult to differentiate between why you are getting that particular electrochemical response from that setup. So the other parameter which is important when we are talking about the working electrode, so I keep talking about working electrode, counter electrode and reference electrode because these are the three most important part, and there is no fixed terminology that which kind of reference electrode can be used for which kind of measurement. Some people use AgAgCl reference electrode, some people use hanging mercury electrode, so there are many different kind of electrodes that you can use, but the important part is when you are taking the measurement, your response is going to get changed when you are going to change the reference electrode. And the kind of for AgCl reference electrode, the solution that we are going to put in that half cell electrode is very important. Some people are using 3 molar, some people are using 3.5 molar, so it is important that we should keep that solution constant, otherwise the response is going to get hampered because the conductivity is going to get changed with that. So when I talk about this whole cell, electrochemical cell, so there are many processes which are forming without the actual response that you are thinking that you are going to get. So one thing was double layer capacitor, the another is charge transfer resistance. So this is the most important parameter when I talk about biosensors or other kind of sensors that we probe using electrochemical system, because the charge transfer resistance actually make us understand how there is a reaction occurring at your electrode, what kind of phenomena are occurring at your working electrode which are going to get changed when you are changing the concentration of the analyte that you are probing. So the next phenomena is the mass transfer phenomena. This is actually the mass transfer phenomena is depend upon how far your ions which are, or the ions in the analyte are from your working electrode, because if they are very far away, then the measurement that you are taking may be very fast and you will not be able to probe those ions. So in that case, most of the researchers, we try to use a magnetic stirrer, so that we stir our electrolyte solution continuously, so that there is a continuous flow of the ions from the electrolyte or from the analyte to your electrode surface that we can measure. So these are some of the phenomena. So talking about, I talk about reference electrode, I talk about working electrode. Another electrode which is also important is a counter electrode. So people have been using platinum electrode, carbon electrode, some other kind of electrode for the for these sensors measurement, but the important parameters that was very important to analyze in the literature was the area of the counter electrode, because when we are measuring something, so we are actually, if you see this thing, we are applying the voltage, the AC voltage with to the working electrode with respect to the reference electrode, but we are actually measuring the current response with respect to the counter electrode. So the area of the counter electrode is very important. If we kept the area of a counter electrode very less as compared to the working electrode, we will not be able to collect all the current that we are supposed to measure, and the response will not be clear, and in some cases you will get that your response is actually saturated and you can't see anything. After a while you will see that you will not see that semi-circular kind of the circles that we are seeing here, or you get just the straight lines. So that may actually be the case that the counter electrode you are using is actually not the exact electrode that you should be using. So for most of the sensing application, the thumb of rule for us was the area the area of the counter electrode should be double the area of the working electrode. So that does not mean the size, we have to increase the size. This way only we are now coming up with spiral models or spring kind of a structure for counter electrodes that we can use. So the effective area for the collection of the current or the collection of the charge should be double of that working electrode. So major benefit I've already talked about it. This is that when we take the EAS measurement, we are actually probing all the processes that are happening at your electrode, but it's very difficult to understand a person who is coming from a non-chemistry background that what is the exact process which is happening. But we can always simulate the processes that are happening in terms of the passive element, that is resistor, capacitor and inductor, and we can always compare when we are changing anything in our system, that how my system is responded to particular probing of or the changing of any variable in my system. So the other thing is, since it's an frequency dependent system and not a time dependent system, so the frequency plays a major role when we are taking the EIS measurements. So in some of the measurement instruments, the range of the frequency which are used is 0.1 millihertz to 100 kilohertz. In some cases it's 0.01 millihertz to 1 megahertz, but we can't go beyond 0.01 millihertz, because in that case the time consumption to take those measurements will be very high, because frequency is inversely proportional to the time. So in that cases, the processes which are very fast, they will not get anything for those kind of processes, and we'll get just a random response for that, and the noise involved in that case will be very high, and we will not be able to differentiate between whether the response is getting due to the slower processes, or is there anything actually happening at the electrode surface. So the frequency is dependent upon the instrument. Different vendors have different kind of machines which offer different kind of frequencies. Another important part is the wiring of electrochemical system. Many researchers, when even me, we did not consider while taking the measurement that the wires that we use, that is connected between my frequency response analyzer and my electrochemical cell, it also possesses some kind of a capacitance. So most of the coaxial cable that we are using, most of the cable that comes with the instrument, they have capacitor in the range of picofarads. So in some cases, either you can go for triax cables or the cables which have very less capacitance, because in some cases the response of your device also come in that picofarad range, and the response of your wire is also in the picofarad range. Either to start with, you compensate for these capacitance or the resistance of these wires that you use to take the measurement, or always try to keep those things constant while taking the measurement, so that these things do not affect. And while taking a low frequency measurement, the probes or the wiring of the electrochemical system is very important. Try to use triaxial cable as compared to other cables. So the last thing is the stability of the electrochemical system. If the system under probe is not stable, and there are many processes which are continuously happening in your system, the measurement that we are going to take will never be repeated. In that case, it's very difficult to understand whatever response we are getting. Is this actually the response of that electrochemical system, or we are getting some weird noise signal due to the electrode interaction only. So the graphs that we have seen as the end result of an EIS measurement is the Nyquist plot and the Bode plot. We try to use a Nyquist plot, and they actually comes as a semicircular graphs. So the most queries that I got from my juniors when I was doing this EIS was that we are not getting those semicircular these semicircular graphs. So there should not, there is not always a case that you will always get these semicircular graph. These semicircular graph means something, and this is based upon the time time constant, and they are actually dependent upon the resistance and capacitance of the system. So your tau value or the time constant, for different processes the RC value is different. So not in all the cases you will get the semicircular graph. You will get the semicircular graph only if the 2 pi fp tau value is equals to 1 or it's greater than 1. Only in that case you will get the semicircular graph, because your system has a capability to probe the processes which are actually happening in your system. Otherwise there will be a Warburg component which will be involved in the processes, and will not get the semicircular graph. Also, as I have shown in this first graph, that there is not always that we'll get only one semicircular graph. We may get many semicircular graph, because there may be many processes which are happening in the system. So for both these processes, the value of time constant will be different. So the semicircular or the semicircle graphs, they will be depending upon the time constant for both the processes. And if we think that there will be a semicircular graph, in that case the first process time constant should be greater than the second process time constant. So these are the important parameters. So before we schedule our EIS measurement, these are some of the components that we try to understand, that these components should be there. Before I take the measurement, I should know my frequency range, and there is no single theoretical measurement which can tell us that this frequency range is going to be the best range for my measurement. So we have to trial and run and understand in which range or which kind of passive element is going to occur in my process, so that I can use the frequency based upon that. So as I said, it's the signals, the input signal or the output signal that we are measuring, they are actually not the time dependent signal, they are actually the sinusoidal signal. So in terms, so what is actually a sinusoidal signal? This is actually an xt signal, which is so this is actually the projection of a rotating vector of length x naught. If you see in that graph, this is normally a sine wave which has some instantaneous value x naught, and it has some frequency, that is, it is getting repeated itself after a while. So when we are probing our signal, that means our signal is actually getting repeated based upon our frequency values. So when we are taking the measurement, there will not always be a case that the amplitude of the output signal will be same as the input signal, or the phase of the output signal will be same as the input signal. So your response can be changed based upon the amplitude and based upon the phase value. That is why in case of the lower figure, I have shown two different sinusoidal things, in which one wave is actually lagging behind the other one because there is a shift in the phase value, whereas the amplitude of this signal is same as the input signal. So while taking the measurement, if it's an resistive element and there is no capacitor or an inductor parameter involved, then in that case the amplitude change will actually give us an indication about the response of the device. But if there is an capacitor or an inductor value involved, then in that case there will be a lagging of signal. The current and the voltage will lag behind each other based upon whether there is an capacitive or an inductive element involved in the process. So how we take the measurement? Basically for an EAS measurement, we have a frequency response analyzer. So we actually superimpose a very small, I actually miss a very important point. So while taking the measurement, it is very important the AC signal that you are using should be of very less amplitude, and we should not use a very high amplitude value, because that if we use a very high amplitude AC values, it can actually store some charges from the electrolyte over the electrode surface, and we'll not get the response which we actually want to see. So the value of the AC signal that we are applying to our system should be very less. So in case of frequency response analyzer, we are superimposing an AC signal over a DC voltage, and we apply this as an input to the electrochemical cell as well as to the correlator or to the output circuit, so that we can measure the in phase as well as out of phase element for our input signal, and based upon the change in the phase and change of the amplitude, we'll actually fit the equivalent resistive circuit or resistive capacitance, or the combination of resistive, capacitive or inductive elements in case of a circuit. So the graph on the right is actually the accuracy contour plot. So this is the basic setup for a frequency response analyzer, but there will be a case that you will be using some other instrument from some other vendor, and I'll be using some other instrument. So when we talk about comparing our response for a measurement setup while keeping all the stuff constant for our measurement, it is then we can compare our response based upon the accuracy contour plot. We take the measurement, and if we measure the body plot with our measurement, if the response, we both are like two different parties are getting, comes into that blue zone, that is your chi-square value is between 0.3 to 1%, that means that response can be repeatable, and the response that we are getting is actually the response of the of your system under probing, and not from some noise that we are getting. And if you are in the gray zone, there are some noise involvement which may be coming due to some connection leak or something that needs to be fixed. And if you are beyond that into the white zone, that means the measurement we are taking, all the parameters are not constant, and there are a lot of inductance or low impedance element which comes from the connections or the reference electrode or the counter electrode that you are using. So the elements are not constant in that case, and the measurement, there are very less chances that this kind of measurement can be repeated. So as I said, since in case of any different kind of element which are involved in the EAS measurement are the three important parameters. One is the resistance, capacitor and the inductor. So I have already discussed that how that in case of capacitor and inductor there is an phase shift between your current and the voltage values. But if I want to see them as in terms of Nyquist and body plot in case of first graph, since in case of resistance there is just a shift in the amplitude value and there is no phase value, you can see just the dot on the x-axis, which is actually the resistance of your bulk or resistance of the electrolyte that you are seeing, and there is no other charging or discharging or any accumulation of any ion from the electrolyte over the electrode surface is observed. In case of a capacitive signal, I am talking about all the ideal cases. There is no resistance or no other element involved. So in case of a capacitor, since if you apply a DC to a capacitor, there will be no current flow. So it's just like a simple line over the y-axis or just some dots which indicate that it's a capacitive element. Next is the inductive element. Since again in this case the response is slightly different, because for some initially it will not conduct any current, it work just as a resistor, but after a while it will start conducting. So that is why you see a shifted y-axis kind of a curve over there. So these are some of the basic elements that we are going to use when we are going to analyze the actual circuit. These are just the basic ideal element that we talk about in our electric circuit theories. So this is a combination of the circuit. So all the semicircular graph that we are seeing, they are actually the combination of resistor and the capacitive elements. So in first case, if it's a complete pure RC circuit, in that case your graph start from 0, which means there is no involvement or no resistance of any kind of electrolyte is observed. In case of second graph, as you see, the R0 value is actually the resistance of your bulk or resistance of the electrolyte. That is why there is a shifting of these curves on the x-axis, and you get the semicircular graph as a response of the RC circuit, but the initial R0 is actually your bulk resistance or the electrolyte resistance. In case of second, there are two parallel RC circuits, so we see two semicircular graph over here, and that shift on the x-axis is due to the R0 value. So these are the important parameters. So these are some of the basic models that we can use to analyze the system under test, but these are not the only element. We can always add more and more element that you can add in your equivalent circuit, the more processes that you can explore. So that is one of the drawback of EIS, that in some cases you add more element, but you don't understand what are the actual processes corresponding to those elements that you are adding in your equivalent circuit. So we start with the bare minimum, we start with the basic RC circuit, then we keep on increasing the capacitor or the resistor value based upon which phenomena are actually occurring in your cell. So coming to this part, so I start with that most of us, when I start doing EIS, for me the electrochemical cell consists of 3 electrode system, but now we are coming up with more different kind of system. So it's not always 3 electrode 4 terminal system. In case of 3 electrode 4 terminal system, that is a new instrument that are coming. They comes with working electrode, counter electrode, reference electrode, as well as a force electrode or a sense electrode. And if you are going to take a measurement using a 3 electrode system, the sense electrode or the force electrode should be combined or shorted with your working electrode, and the other 2 electrode can be used as it is. So that is the first thing that you can see. In case of a 2 electrode 2 terminal system, since for to probe the batteries, it is very important which kind of electrode system you are using, because using a 2 electrode system and 4 electrode system will have very separate kind of response, and it is very difficult to understand which equivalent circuit can be fit in both the cases. So keeping that in mind, it is important to use the relevant electrode combinations in your measurement. For a very sensitive measurement, never use a 2 electrode system, because in that case the noise will be very high, and a lot of data will be missed because of that. In that case 3 electrode system can be used. Coming to the 4 electrode system, again this is most important electrode system that currently we are using for the battery measurement for the charging and discharging part. So how our response on, then I talk about all the double layer capacitance that we are seeing, or the bulk resistance. So that is if I am putting my working electrode inside an electrolyte solution, there are many ions which are present in your electrolyte solution. So some are present near the electrode, which is actually in the IHP, that is the inner Helmholtz plane. Some are away from the electrode, which are from the outer Helmholtz plane, which will actually leads to the formation of double layer capacitance, because they tend to come near the electrode surface. Whereas your charge transfer resistance that I discussed at the beginning, they are due to all the ions which are actually very near to your electrode surface, and the mass diffusion component that I talk about is due to all the ions which are very away from the electrolyte system. So basic RC circuit that we are seeing in a Nyquist plot, they are actually the combination of this process happening at your electrode, and the value of, as you can see, for the analyte your value depend upon the conductivity of your electrolyte, whereas for the charge transfer resistance it's actually a temperature dependent process. So it is important to keep the environment of the room also constant when you are taking the measurement, whereas a charge double layer capacitance, it's actually depend upon the interaction of the ions with the electrode surface and the voltage that we are applying for the measurement. So coming to the case studies for batteries, since this is like one of the basic model that I have kept, this is a lithium ion batteries. So in case of lithium ion batteries, there is an cathode, there is an anode, and there is an electrolyte which is kept between these two, and there is a separator. So based upon all the processes which are happening inside our batteries, the green graph is actually the ideal case that we should see in our as a response of our measurement, but we are not seeing this graph, but we are seeing the actual graph on the pink one, because of there are so many processes which are involving, and the frequency at which these processes are occurring, they're actually overlapping. So that is why we are not able to take those to understand those measurements. So that is why it's a very slow process. So it is important the frequency range in which we are taking the measurement should be such that all the processes which are happening should come and should be covered in that frequency range. So but that is the practical response of the batteries when it comes to the EAS measurement. So next are the biosensor. In case of biosensor, most commonly used biosensor are the capacitive biosensor, which are actually the combination of antigen antibodies. So if you see on the left, in case of antigen and antibodies, we are actually putting the antibodies over a conducting substrate or a 2D material, and when there is an interaction of antigen and antibody, they are actually forming a capacitive kind of a structure. So that capacitance can be seen in terms of the Nyquist plot, and when we are changing the concentration of the analyte in the electrolyte, then there will be a shift in the Nyquist plot on the y-axis, that is the imaginary axis, which means the capacitance is of that system is actually getting changed when we are changing the number of ions in our analyte based upon the molarity or based upon the concentration of the antigens that we are using. So that capacitance that we are seeing, in that case, ideally, if you see so many capacitance, ideally there should be multiple semicircular graph, but we are seeing just one semicircular graph. It is because the resistance involved in this case is very, very less, and there is no combination of RC circuit. This is actually the capacitive circuit, and in this capacitive circuit, just like the resistance, the Kirchhoff's law, they also apply. So this capacitance that we are seeing is actually the impedance, and it also get added same as the resistive values. That is why the change in the capacitance is actually addition of all the capacitance that we are seeing with the change of the analyte concentration. That is why you see the shift in the capacitance value on the imaginary axis and nothing on the x-axis, or there are no multiple plots that we see on the x-axis. So next come to the water monitoring. This is my work that I have covered. So in one case is we have actually used a CDSE nanoplatelet for the sensing of cadmium ion. In this case you see that I don't see much on the y-axis, but my change on the x-axis is very high. This is because there is an interaction between cadmium ion and the CDSE nanoplatelet, and they are actually getting attached over the CDSE nanoplatelet and changing the resistance of that nanoplatelet. That is why with the shift, my charge transfer resistance was actually getting changed, and the response that I get as a response of the change in the concentration of cadmium ion is actually in terms of charge transfer resistance and not the double layer capacitance, because there was no charge accumulation or charging or discharging of my electrode. There was actually the binding of cadmium ion over the CDSE nanoplatelet that I was using as a working electrode. So next setup that we have done was for the copper ion sensing using cadmium sulfide film. So in that case we have used a chemical bar deposited CDS film over a gold electrode, which was our working electrode. We use a 3 electrode system and take the potentiometric measurement. In some cases the potentiometric measurement that we were getting, it was not getting repeated. So in that case I have mentioned already, so the electrolyte concentration that we were using, the conductance of that electrolyte was not appropriate, and that we get as the response of an EAS measurement that we took initially. But once we sorted this out, we see that in this case in this case there was just the charge transfer resistance change, but in this case there was also a change of a double layer capacitance, because that CDS film was actually porous and there were a lot of cadmium ion from the water which are getting accumulated over my working electrode surface. That is why you see the change in the imaginary axis as well as on the real axis. So based upon that we concluded that the CDSE film was actually accumulating and the surface of my CDS film was changing. So that CDS film was actually forming a copper sulfide film on the top, and the interaction which was happening between the copper ion in the electrolyte solution and my surface was not between CDS and copper, but it was on the copper sulfate and CDS heterostructure which was forming as the response of the reaction of copper with cadmium ion. So in that case the Nyquist plot actually help us understand the change in the stoichiometry of our sensing film. So we were able to understand it in the form of R and C circuits. So these are some of the complexity of using an EAS measurements. It's sometimes because there are so many equivalent circuit which are present, and it's very difficult that which circuit is the best circuit for my measurement, then sometimes it's very difficult to understand or analyze this complex data. The second point is actually related to the biosensor. There are many non-specific changes that happen at the surface of the electrode because of the oxidation of that electrode as a response of the electrolyte environment in which we are keeping our cell. Next is a limited frequency range. In some cases the instrument that we are using or the wires that we are using, it actually restricts us to use a frequency range, and sometimes the processes are so fast that it is very difficult to analyze the response of the device in that in lower frequency regime or higher frequency regime. So in that case EAS is of no use for some of the applications. In some cases the sample requirement is again an issue for some of these measurements, because if I talk about the liquid electrolyte, we have to make a bigger electrolyte cell and you have to take a lot of electrolyte solution. But in some cases for example in biosensor, the samples that we are getting, it's not in the milliliter, they are actually in the microliter. So it is very important to use them or repeat those measurements with these kind of samples. So in that case it's better to take the measurement which will give a faster response as compared to the EAS measurement. So again the last is the model limitation, that if there is some unique combination of these passive element which is there and we are not able to understand based upon any circuit which are present in your software, then it will be very difficult for the researcher to understand that how we can probe our system and what is the equivalent circuit for that particular model. So these are the references that I have covered.